Okay, so Junwei, I'll after about 20 minutes have passed, I'll give you sort of a warning. You have a few minutes left.
All right. Okay, let's start. So first of all, I would like to thank the organizing committee to give me this opportunity to speak in front of you. The SDO has been 11 years old. It has been 11 amazing years. The HMI has continued observations for almost 11 years. And we have made great achievements in many aspects regarding the solar interior dynamics and the magnetic dynamics. Here, I would include a few topics that I'm familiar with. I cannot cover everything. I can only cover something I'm familiar with. So this includes differential rotation, meridional circulation, helioseismic central limit effect, flows in active regions, fast imaging, and Sunquakes. There are other two topics I had planned to speak, but I will leave this opportunity to the other two speakers, Lisa and Aaron. So let's start with solar rotations. The biggest change in the last 10 years of the sun, I think, from my point of view, is the rotation change. In 2018, Rachel Howe reported that the sun's interior rotation speeds increased a lot below 30 degrees latitude and slowed down dramatically above that latitude. Similarly, Sabani Basu and Antia, they reported a similar finding. What's shown here, let me bring the laser pointer here. What's shown here is from GAN results, but they confirmed Rachel Howe's findings. That is, the sun in the high latitudes, the solar rotation slowed down significantly, but in the low latitudes, the speed up is a little bit is pretty slight. So looking at these results, these observation facts give us some great challenges mostly to theorists. So these questions we want to ask is, what causes the slowdown of the solar rotation above the middle latitude? What does this mean to the solar dynamo and magnetic cycles? The other question we face is what transports the huge angular momentum from high to low latitudes? Probably the meridional circulation plays a role here, but does the equatorward meridional flow sufficient? Is it sufficient for the transportation? Is there any other mechanism to play a role here in the transportation of the angular momentum? So these are the challenges we're going to face in the next few years. Now, let me move on to a slightly different topic, torsional oscillations. Once again, Rachel Howe, in her 2018 paper, reported the torsional oscillation patterns in the cycle 23 and cycle 24. So look at here. If you can see my laser pointer is here. If you see this fast band, torsional oscillation fast band corresponds to cycle 25. Compared with the fast bands corresponding to cycle 24, the current band is a lot weaker than the previous one. Does this mean cycle 25 is going to be weaker than 24? Similarly, by use of the time distance helioseismic analysis and HMI data, we are also able to excuse me. We are also able to map the torsional oscillation patterns near the sun's surface. But more importantly, the local helioseismology is able to give us the southern hemisphere and the northern hemisphere patterns separately. Look at the southern hemisphere. The torsional oscillation bands is started a little bit earlier and stronger in the southern hemisphere. Does this mean the southern hemisphere will have a stronger activity cycle for the next one? We don't know. Dynamo waves. So also 2 years ago, Sasha and his collaborator, Valerie Pippin, they used the deceleration of zonal flows to indicate the magnetic locations inside the sun. They call it as dynamo waves. Let's look at this location. Location C. This location is at roughly 60 degrees latitude and at the base of the convection zone, tachocline. They believe this was the starting point of the dynamo operation for the next cycle. So this location corresponds to cycle 24. And 10 years later, just below at the bottom panel, if you look at here, the similar location, we say the dynamo operation for the cycle 25. If we compare the deceleration magnitude, this one is a lot smaller than the previous one. Does this mean cycle 25 is going to be weaker? So there are some few challenge questions facing us for the next few years, particularly for the theorists and modelers. Can the magnitude of torsion oscillations or zonal decelerations be an indicator to the magnetic activity level of the next cycle of cycles? What determines the magnitude of torsion oscillations? So now let's move on to the second topic, meridional circulation. First of all, I really want to emphasize this point. The HMI observations, together with the discovery of a systematic central limit effect, enables us to detect the equatorward flow. Many people care about how many circulation cells are there inside the sun, but let's recognize the first fact. HMI enables us to find the equatorward flow. Before the HMI, this was not doable without further constraints of some other physical conditions. So this is the first detection of equatorward flow the HMI brought to us. I also want to point out, so far, the most time-distance helioseismic analysis about meridional circulation, they used the equatorial measurements as a proxy of the central limit effect. They just subtract the central limit, the east-west measurements from the north-south measurements. But there is one notable exception. This was done by Rachel Chen and myself. We developed a comprehensive measurement scheme that made measurements across the solar disk, and then disentangled the flow-induced signals from the central limit effect. Here, we showed the results from the hemisphere symmetrized meridional circulation using HMI's 7-year observations. What is shown here is basically 3-layer flow structures. This is a poleward flow, this is equatorward flow, and this poleward flow again. This indicates a double cell circulation from this analysis. So we also recognize there are different results from different scientists. Here, I listed 5 sets of results from 5 papers. We recognize the differences, and then we organized an EC workshop in 2017 in Bern, Switzerland, to discuss these differences and discrepancies. One conclusion from that workshop is the discrepancies are mostly due to the acoustic travel time measurements, not the inversions. Furthermore, Vincent Boyning in his paper pointed out that the wave of ray approximation kernels might not be responsible for the discrepancies either. So mostly we have to focus our next step to solve the discrepancies on the travel time measurements. So putting aside the discrepancies among these results, we also have some agreements. First of all, we all find the equatorward flows from all these measurements as results. So this is the first important agreement. There's another small yet very important consensus. That is, in low latitude areas, roughly below 20 degrees latitude. So all these 5 sets of inversion results showed multiple cell circulations. So why do I think this is a very important consensus? Because we have to confront the numerical simulations. There are a lot of quite a few numerical modelers doing simulation inside the sun. For example, this one. This is a result from Nick Featherstone and Mark Misch in their 2015 paper. I also recognize there are some other modelers like Agustova and some others. They have similar results. So look at, for example, look at this, this plot in low latitude areas below about 20 degrees. So they also show a multiple cell circulation. So compare with these 5 sets of observations with the numerical models, we found some similarities. This is a very, very important consensus from my point of view. Certainly, the optimism just stopped here. We also recognize by looking at the different higher latitudes, the global convection simulation, they show they show a solid body, just a bulk of convection. But the other thing is the observation inversions. They often show spherical shell structures, regardless of single or double cells. So there's a lot to do to reconcile models and observations. There's also a new twist. Last year, Laurent Gizan and his collaborators, they used the GONG and SOHO MDI's 2 solar cycles observations for their study. They found a single cell circulation. They also compared HMI observations with GONG and MDI observations. So look at these red curves. These red curves have a systematic offset from the compared with the other 2. So I call them as the cross-equator signals. Noticeably, the cross-equator signals, they do not just exist in the HMI observations. They also exist in GONG and MDI results. These are from also from Laurent's paper. So if we look at these highlighted areas, we can clearly say the cross-equator signals. That means cross-equator signal is not just from HMI, but also from other instruments. The thing is, HMI's signal is a bit larger than the other instruments. So this also poses another challenge to our understanding of the sun's interior circulation, for sure. So far, what I have introduced are mostly time-distance helioseismology analysis about meridional circulation. We also recognize there are other methods doing similar stuff. For example, David Hathaway, in his 2012 ABJ paper, he used supergranules as probes. In this paper, he reported that a significant equatorward flow, about 4.6 meters per second, were found corresponding to a depth of about 70 megameters. So another analysis by using the global helioseismology method. So this is not local helioseismology, but global helioseismology. Adriani, Shad, and her collaborators, they had a conclusion like the flow profile had a complex spatial structure consisting of multiple flow cells distributed in depth and latitude. So what I want to point out is they used MDI data for this analysis, not HMI. More recently, actually this was just from last week, Doug Brown and his collaborators posted this article in arXiv. They used Fourier-Lisandre decomposition and analyzed 88 months of HMI data. They inferred the presence of a equatorward flow at a depth of approximately 40 megameters below the photosphere. That is a lot shallower than others, but they also point out that they may not be able to inadequately remove the systematic errors in the HMI data. So I want to emphasize all these three results from different methods. They all point to a shallow equatorward flow. Of course, the Brown et al. They cautioned the reliability of their inference. So the challenges that face us in regarding the meridional circulation, the first thing is how to reconcile results from different sciences. From my personal point of view, the first thing to do is to compare acoustic travel time fitting method. The second thing to do is to refine the central limit effect removal method. And the third thing is to incorporate wave-based sensitivity kernels. These wave-based sensitivity kernels are already available from different authors. Next question following is naturally, even if all helioseismologists reach a consensus, does it mean that we know the sun's interior circulation? My point of view is probably not. A small error in systematics can cause a large mistake in the inference of meridional circulation. We need to be very careful. How to understand the cross-equator signals observed in HMI? This is a question we are going to face for the next few years, I guess. What can we do to reconcile observations with the numerical modeling? We need a collaboration between modelers and observers. So there is a long way to go before we fully understand the sun's circulation. Let's move a little bit to the shallower region, the temporal evolution of the near-surface meridional circulation. Like the zonal flows, residual meridional flow also shows the migrating faster and slower bands. Actually, the faster means poleward and slower means equatorward. So this is also from HMI, time distance pipeline. So look at, this is the bands corresponding to cycle 24. And these contours show locations of magnetic fields. Look at, this is already, the bands corresponding to cycle 25 already appeared before 2016. The southern hemisphere showed a stronger pattern and in magnitude larger than the northern hemisphere. Does it mean in 2025, cycle 25, southern hemisphere is going to be more active? We're not sure. But what I want to caution is the magnetic impacts on the flow pattern. To study how active regions modulate the meridional circulation pattern, Sushan, Mahayang, and Xudong Sun, they exclude the regions of different distances from the active regions. For example, if they only use the signals within 5 degrees from the active region, they got the meridional circulation pattern like this. If they exclude 5 degrees from the active region, they got the meridional flow pattern of the last 10 years like this. We can still clearly say the magnetic modulation in this flow structures. However, if they expand the distance from the active regions, for example, 22.5 degrees away from the active regions, basically what they got is the meridional flow near the surface remains relatively flat without much change. This demonstrates the modulation from active regions can reach up to a distance of 20 degrees. Similarly, below, Rudy Combe used the Venn diagram results of 2 solar cycles. They analyzed the flow patterns with and without magnetized regions. No wonder the magnetic field did modulate the flow patterns of the meridional circulation. So the challenges we face, if the meridional flow pattern is largely modulated by magnetic field, is the zonal flow pattern also modulated by magnetic field? I think the answer is yes, but to what extent needs some more exploration. Putting aside the magnetic modulation, is the meridional flow pattern indicative to the activity level of the next cycle? This is a similar question facing zonal flows. So now let me move on to the central limit effect. The helioseismic central limit effect is basically a travel time asymmetry for waves traveling between two locations, but along opposite directions. For waves traveling from A to B and then from B to A, the measured travel times are different. They are not equal. So this is the travel time asymmetry we call central limit effect. This effect is highly latitude, distance, and frequency dependent. Its magnitude is about 1 order of magnitude stronger than meridional flow-induced signal. So what causes this systematic effect? Despite some promising proposals to understand this effect is yet to be fully understood. Its correction so far is mostly empirical. So look at this plot. Point A and point B, they are different. Because of the limb darkening, the line formation height is different. Line formed a little bit higher in point A than in point B. So the central limit effect is essentially due to the different atmospheric heights where oscillation signals are taken for travel time measurements. Talking about different atmospheric heights, that reminds us something different. Another thing.
Anyway, you have a few minutes left.
Thank you. This is the travel time asymmetry in the sunspot regions. Due to Wilson depression, the time distance helioseismic measurements in and around the sunspot regions are also made using signals from different heights. Umbras are lower and quiescent are higher. Could this cause a systematic travel time asymmetry? Our measurements using the observations near sunspots give this frequency dependence, which is very similar to the frequency dependence for the central limit effect. I use the opposite color table here, so be careful. So they are very similar. So this may demonstrate that the atmospheric height difference accounts for, at least partly, the travel time asymmetries in sunspot regions. So 2 years ago, Doug Brown, using holography methods, he derived averaged flows. He derived flow structures around averaged sunspots. The averaged sunspots are then categorized into different sizes. Similarly, Mahayang and Sun, they obtained flows of averaged sunspots using HMI, time-distance pipeline results. These two sets of different results from different methods show very similar flow patterns. However, my question is, how much can we trust these flow structures? Because these inferences haven't accounted for the travel time asymmetries caused by the atmospheric height differences. So the challenges facing us is what's the physics behind the central limit effect? What is the best strategy to remove this effect? The atmospheric height difference partly accounts for the travel time asymmetries around active regions. Is there a method to remove this effect, even an empirical one? Personally, I doubt. I don't have any good solution for this. I have thought about this for a while. So is it possible the cross-equator signals in HMI is due to the same effect? Very likely. The HMI spectrum line is more sensitive to this effect. As we understand, the central limit effect from the HMI is about twice large as it from the MDR and the GAN. So this gives us some hints for the next years to work on. Let me move on to the far side images. So 2 years ago, myself and my collaborators, we developed a new far side imaging code that's able to monitor emergence and evolution of active regions on the far side of the sun with higher reliability. Look at this example of last November. So here, we saw an emergence of active region on the far side. This is the far side. This is the near side magnetic field. So we saw this emergence. A few days later, this new emergence grew into a huge active region. Yet a few days more, this huge active region appeared on the near side. So this new method complements the existing holography far side method developed by Charlie Lindsay and Doug Brown. I believe together, this new method with the old method, with these two methods, we are able to monitor the far side active regions with higher reliability. Furthermore, we did some machine learning work. Rachel Chen developed a machine learning code that's able to convert stereo far side images into magnetic flux maps. This method is very similar to Kim et al. Developed in 2019. So we were able to convert stereo far side UV images into far side magnetic flux maps. Meanwhile, we have tons and tons of far side acoustic images. Combining the far side, this flux map together with this far side acoustic image, we are able to develop a second machine learning code to convert the far side acoustic image into this far side magnetic flux map. So this is amazing. This means we use near side Dopplerograms as an input. We're able to get the far side magnetic flux from as an output. So the challenges that we are going to face for the next few years is, can we further improve the far side imaging technique to map smaller active regions? If we can map the far side magnetic flux, can we map the far side magnetic field? Okay, let me move on to very quickly, very briefly, the last topic. So Rachel Chen and I surveyed most of the M6 plus flares in cycle 24, and we identified 41 Sunquakes in 24 active regions. But most of solar flares do not generate Sunquake events. Why is that? Our analysis found that more than 80% of Sunquakes were excited at locations where flares impacts coincide with the downward oscillations. So the sun has oscillations everywhere. So it's upward and it's downward. If a flare impact coincides with a downward wave, a downward oscillation, so this possibly can make the waves more stand out. So this is a possible selection rule to tell us which flare may possibly excite sunquakes. There's another very exciting sunquake event. The X9.3 flare generated the strongest sunquake event that was ever recorded. By use of HMI's continuum intensity observations, line core intensity observations, and Doppler velocity observations, we're able to monitor the expansion of the sunquake waves as ripples across the solar disk. More importantly, we are also able to follow we are also find the waves have caused the magnetic field to changes. This is a wave of magnetic variation with a magnitude of 40 Gauss. So this is the first time we saw such an event, and this so far is the only one that causes magnetic field to change. So the challenges we face: can we predict whether or where a sunquake will occur and how strong it will be? If we can, that demonstrates that we understand well both the flare dynamics and solar oscillations. What can we learn from magnetic sunquake waves? What causes the waves of the magnetic variations? So this is my last page. I summarize all the important points from the topics I mentioned. Okay, thank you for your attention. I will stop here.
Thank you very much, Junwei, for that nice summary of progress and challenges.